Let's begin with an overview of Conflux. There are some core elements here. So the first element is the tree graph algorithm. Conflux employs a very innovative consensus algorithm that enables it to process blocks in parallel, which is a key for its actual throughput. This reduces both confirmation times and increases transactions per second, which provides both speed and reliability. Next, we have the GHAST selection rule. Conflux replaces the traditional longest chain rule with the GHAST rule. This rule allows Conflux to prevent liveness attacks by enabling the dynamic adjustment of the block weights and block types. This is quite an interesting topic. We will go deeper into this in a few moments. Next, we have this hybrid proof of work plus proof of stake consensus. This is another key element of Conflux in terms that it can combine both the security and reliability of proof of work with the efficiency of proof of stake. And this approach is also fundamental for making Conflux what it is, actually. And the final element is the spaces. As some of you might know, Conflux has two different spaces. One is called core space and the other one is called e-space. So core space is the original chain and it actually provides more throughput, while e-space is a space designed to be fully compatible with Ethereum virtual machine. So we will also go deeper into all of these topics in a couple of minutes. First of all, let's start with the tree graph algorithm. Well, here you can see an image which is a representation of the tree graph, but basically at the heart of Conflux there is this tree graph ledger structure and the GHAST selection rule. This structure is called the tree graph. So each block not only has a single parent, but it also keeps a list of all the references to previous blocks. So you can see that each block here on the chart has parent edges and reference edges. So having this list of references to previous blocks provides very valuable information about the order in which blocks are created. So when transactions come into play, Conflux employs the GHAST rule to choose the pivot chain. So once the pivot chain is selected in the tree graph, then by using this pivot chain and the references between blocks, Conflux arranges all the blocks in a linear sequence. So this sequence determines the order in which transactions are executed. This is basically one of the biggest innovations in Conflux network and is kind of the key of making it has the throughput and the scalability it actually has. Now let's talk about the GHAST selection rule. This is actually a very clever solution developed by the Conflux research group, which is focused on preventing liveness attack. GHAST means greatest, heaviest adaptive subtree, as the name here displayed on the slide. Basically, traditional blockchains like Bitcoin or Ethereum follow a rule in which only the longest chain survives, while the other chains are discarded, let's say. So this approach creates a conflict between scalability and security. This is where the GHAST mechanism comes, in which Conflux basically takes a different path, a different approach. Conflux replaces the longest chain rule with the new GHAST rule. This makes the selection process much stronger and robust. Instead of relying solely on the number of blocks, the block type is determined based on the historical structure of the tree graph. With the GHAST rule, the heaviest chain rule is used, but there is a modification on the block weight system. So this is where the interesting innovation comes. Basically, with the GHAST mechanism, we have different block types and also different block weights. There is two different types of blocks. There is normal blocks and there is special blocks. In the absence of an attack, all newly generated blocks are just normal blocks. But if an attacker conducts a liveness attack, all newly generated blocks will become special blocks and they will have a different weight. So this increases the difficulty and prevents liveness attacks from happening. Basically, incorporating these different block weights and block types, Conflux has the capability to maintain its security even under challenging circumstances. Next, we will talk about the spaces. Conflux has two independent spaces. There is the core space and the e-space. Core space is the original chain and provides more network capacity. It wasn't called core space before. We changed the name after e-space was created, but actually before it was only Conflux network. So this is the original chain and it has a higher throughput and has the ability to support gas sponsorship, but has some differences compared to, let's say, Ethereum. It has a different address notation, it has different tools. You need to use Conflux Truffle, Conflux Hard Hat. You need to use Conflux official SDKs. That's where ESpace comes, which is fully EVM compatible. This is basically a virtualized Ethereum chain inside of Conflux. But the difference here in terms of throughput is that block time is twice as core space, so it's lower, let's say. But actually, it's really fast anyway, and both of them are really cheap in terms of the gas fees. And both of these are logically independent. Let's say they have their own transactions, their own contracts, their own addresses, but there is a link between them, which is mostly based on this cross-space called internal contract that enables communication between these spaces, which means that you can, for example, deploy a contract on ESpace from core space, or transfer CFX from core space to ESpace, or call methods from a contract on ESpace from core space. So it's a key element in this space's innovation. And it's also important to note that these spaces, even if they are independent logically, they share the same layer of consensus. Proof of work and proof of stake works for both of them. Now let's talk about consensus mechanisms. First, we have proof of work, which is the most known because of Bitcoin probably. But we all know that proof of work works. We know it's reliable and security. Basically, proof of work is a consensus algorithm used by blockchain networks like Bitcoin, and it was used by Ethereum before. It involves miners solving puzzles that in order to add blocks, and this results in quite a secure and reliable blockchain network. First, miners solve the puzzle and add the block. Then for doing so, they are rewarded with cryptocurrencies. In the case of Conflux, of course, it's with CFX. But Conflux implementation of proof of work has some differences, the tree graph algorithm and the GHAST rule. This reduces the chance of forks and ensures kind of faster transaction confirmation compared to other proof of work networks. Apart from proof of work, also Conflux added proof of stake finality layer. This is also related to improving confirmation speed and resisting potential 51% attacks. We know, for example, that before Ethereum migrated from proof of work to proof of stake, there was a huge computational power in terms of GPUs mining Ethereum. So there was a high risk of, let's say, a huge mining pool to migrate to Conflux and have a high percentage of the hash power. So actually the risks for a smaller blockchain like Conflux of being attacked with 51% attacks is higher than it is, for example, for Bitcoin. This layer actually increases the security by providing an independent finality decision, which is taken in a random way based on how much CFX you have staked on the staking platform. In POS, attackers cannot execute double spending attacks based just on computing power. They will need to invest enough CFX to influence any POS decision. Having both consensus mechanisms enables Conflux to get the benefits of both. So we got the advantages of the proof of work consensus, which is security and reliability, plus the efficiency of the proof of stake consensus mechanism. So this means high security, fast confirmation, and a reasonable energy consumption.